Welcome to the Lone Star Analysis Condition-Based Maintenance Enabling Technology Tech Talk. Our warfighter pilots depend on cartridge-actuated devices and propellant-actuated devices, also known as CADs and PADs, to provide the explosive charge to safely eject them from failing aircraft. These devices are routinely replaced blindly every 24 months, very often prematurely, without any knowledge of the usable service life left in the device. Even with our life-critical pilot ejection system, which depends on CAD and PAD components, the DoD is facing supply chain challenges for maintenance parts. Imagine having a predictive analytics solution that erases uncertainty, enhances pilot safety, addresses supply shortages, and optimizes budgets. Our innovative technology aims to tackle these challenges head-on. Meet MaxUp Ordain, the key to implementing condition-based maintenance tailored for CADs and PADs. Our technology enables crucial decisions on extending their service life while saving resources, time, and saving lives. But here's the kicker. MaxUp Ordain isn't limited to CADs and PADs. It's scalable across the Department of Defense arsenal. Sponsored by NavAir, this technology allows a shift from reliability-centered maintenance to condition-based maintenance, focusing on energetic components. This digital twin technology is part of our award-winning MaxUp Readiness Suite, offering advanced operational analytics software for optimizing readiness across diverse assets. Today, we'll dive into developing digital replicas for CADs and PADs and updating efforts to make this technology operational in a cloud-based environment. This step ensures you gain immediate insight, speeding up decisions on service life extension. Lone Star Analysis is a provider of applied decision intelligence and engineering solutions. We harness predictive and prescriptive analytics and evolved AI to enhance innovation and create value. Since 2004, organizations have trusted Lone Star Analysis to deliver actionable results addressing complex problems. CADs and PADs are pivotal in aviation safety, performing critical functions such as launching weapons, triggering fire extinguishers, and aiding pilot ejections in emergencies, fundamental for safeguarding the lives of naval aviators. Despite their significance, the Navy contends with persistent challenges like shortages, outdated parts, failed lots, and delivery delays for these crucial components. Currently, there is no accurate way to monitor their health or predict their service life. Consequently, approximately 70,000 CAD and PAD parts are replaced annually, even though many are likely still in usable states. For safety reasons, conservative limits are set for these components' lifespan, often leading to premature removal of parts with substantial remaining usability. The Precision Strike Weapons Program Office manages 2,500 CAD and PAD types, totaling 380,000 parts on active aircraft. Each type has unique failure patterns, creating safety, cost, and logistics uncertainties. Recent accidental detonations and supply chain issues emphasize the urgency of managing these safety-critical items differently. Illustrated here is a 2007 MT-29 parachute deployment rocket motor that unexpectedly detonated in an FA-18 hangar. Although there were no fatalities, such unplanned detonations always pose severe risks. In search of a more efficient approach to CAD and PAD lifecycle management, the Navy is seeking digital twin technologies to provide predictive and prescriptive capabilities for designing, developing, sustaining, and disposing of these critical safety items. For this project, the term digital twins means digital representations of actual CADs and PADs installed on Navy aircraft, serving as digital counterparts for modeling and simulation purposes. The objective of the digital twins is to assist Navy personnel in understanding environmental impacts on component performance and service life. To meet the established CAD and PAD challenge, SBIR or SBIR research is to focus on addressing four primary questions. Can digital twins provide accurate assessments of remaining service life? Is the currently established 24-month service life for these components optimal? Can digital twins be effective without installing cockpit sensors? Can the digital twin capability be operationalized within a cloud-based environment? The Navy selected two components integral to the FA-18 ejection seat for prototype digital twin development: the MT-29 parachute deployment rocket motor and the WB-15 cartridge-actuated initiator. Lone Star Analysis developed crucial CAD and PAD digital twins for transitioning from RCM to CBM. These twins specialize in failure analysis, predicting component lifespans by examining stress factors. Given the varied definitions of digital twins, it's vital to note that this CAD and PAD digital twin focuses specifically on failure prediction. These failure twins scrutinize stress accumulation to gauge individual component service life, what is used up, and what remains. MaxUp Ordain forecasts service life for an 84-month period using Navy databases and analyses like thermal studies and weather data. Prototypes have shown accurate service life predictions in government validation, pending further lab tests for full approval. Interestingly, the 24-month service life might not be optimal. Stabilizer depletion varies based on temperature exposure. 24 months may be inadequate in some situations and much too conservative in others. The Lone Star Analysis SBIR aims to implement this digital twin capability securely in the cloud, adhering to IT and security standards. A business analysis compared CAD and PAD RCM with a sensorless digital twin-enabled CBM approach. The findings reveal a substantial 59% yearly cost reduction for MT29 and WB15 components by adopting digital twin technology. Beyond financial gains, there are critical non-financial benefits. Extending component life alleviates CAD and PAD supply challenges, minimizes part delays, and ensures better aircraft operation availability. It also cuts down unnecessary removals, reducing the risk of damage. Fewer removals mean reduced chances of mishandling, enhancing safety for aircrew and maintenance personnel. CAD and PAD service life extensions are increasing rapidly, burdening the program with reviewing and approving change requests. MaxUp Ordain streamlines this process, saving engineering analysis time, aiding approvals, and minimizing database errors. Establishing a fully functional digital twin environment for CADs and PADs aligns with the U.S. Navy's interests. It offers substantial savings, supports congressionally mandated predictive maintenance requirements, and brings positive operational impacts. The figure identified here captures the CAD-PAD digital twin high-level operational concept. MaxUp Ordain resides in the government cloud, where requisite data is uploaded on a government-established recurring drumbeat. In the case of the National Oceanic and Atmospheric Association data source, this data is uploaded automatically without manual support. In the case of the DoD data sources, such as DeckPlate and ClickSense, Lone Star has not been given authorization to directly access the databases, and therefore, reports are downloaded from these sites by a man-in-the-loop for upload into MaxUp Ordain to satisfy data input requirements. After MaxUp Ordain runs the analysis and establishes a baseline, fleet leadership, logisticians, and program managers can run what-if simulations, conduct procurement planning, or evaluate inventory management. As directed by CAD-PAD leadership, the government cloud, where MaxUp Ordain is located, is to remain separate and distinct from the virtual fleet support management tool located on the VFS server, where service life extension analysis is performed by the CAD-PAD engineering team. As a result, monthly MaxUp Ordain model result outputs are submitted to VFS personnel for incorporation into the service life extension model contained in the VFS server. Once complete, service life extensions, investigations, and other analyses can be performed using predictive analytics. The 2022 Direct to Phase 2 SBIR targeted high payoff CAD and PAD candidates, PDRM and WB15. Prototype digital twin models now predict the remaining service life and are in government validation. Moreover, a secure, cloud-based CBM capability accessible via the Navy's network was shown to the government in December 2023 and is operational. The government suggests an SBIR Phase 2.5 to speed up the transition using sensorless capability and cockpit temperature data from NavAir's aircraft. Phase 2.5 aims to test the digital twin service life predictions using actual data, crucial for NavAir SBIR Phase 3 adoption. Comparing predictions with engineered and actual cockpit temperatures is key for technology adoption. Digital twin program funding is established in the Future Years Defense Program. A prioritized list for expanded capability exists. Condition-based maintenance is becoming a reality for CAD and PAD inventory. As confirmed by the Naval Surface Warfare Center Indian Head Division and CAD and PAD Joint Program Office, the digital twin technology is relevant to and is planned for transition to targeted components within the portfolio of managed CADs and PADs. For the MaxUp Ordain prototype delivery, 2 FA-18 devices are currently modeled, but at least 676 other CAD and PAD device types deserve consideration. Every platform within naval aviation utilizes CADs and PADs for multiple purposes and will significantly benefit from the predictive capability. Lone Star Analysis recognizes the value of sensorless digital twin technology as an enabler of condition-based maintenance. It is prepared to first expand the capability within naval aviation and then across DoD. Cloud-based digital twins can be delivered in as little as 4 months, depending on data availability. According to the GAO, the military has made limited progress in implementing condition-based maintenance capabilities until recently. MaxUp Ordain is the catalyst for CAD and PAD predictive maintenance, and we are eager to address your specific needs. Looking to implement condition-based maintenance technology? At Lone Star Analysis, we want to understand your needs and system specifics. Our expertise can assist in enhancing safety measures, resolving supply chain challenges, and cutting down unnecessary expenses. Let us optimize your operations and ensure a more secure, efficient, and cost-effective future. Under SBIR topic N211-D02, Lone Star Analysis has shown digital twins can accurately predict CAD and PAD remaining service life. The RCM established 24-month service life is not optimized for the MT-29 parachute deployment rocket motor and WB-15 cartridge-actuated initiator. Digital twins can be delivered without the burden and cost of modifying cockpits with temperature sensors. Digital twin capability can be operationalized within a cloud-based environment. Reach out today to request a one-on-one demonstration. Let's explore how Lone Star Analysis can help your organization. We deliver decision superiority. For further information, please reach out to Dave Padula, Strategic Account Manager for Lone Star Analysis.